Hello everyone, my name is Clancy Blenkinsop and I'll be presenting to you on my master's thesis research project, dust deposition on an underside. This was completed with the WA System Health Lab and I was supervised by Quentin Thomas and Professor Belinda Hodkowitz. First, just a bit of background. So dust is a major byproduct of mineral extraction and processing processes, being crushing, haulage, and conveyance are common across these kinds of operations. And this can be a major reliability issue for many laser and camera-based systems, which rely on a clear line of sight. So these include things such as LiDAR used on haulage trucks, plant surveillance for remote operators, computer vision for automated systems, as well as condition monitoring systems, such as the one we'll be discussing today. So the Warehawk is a condition monitoring system for conveyor belts. It involves positioning a row of cameras on the back end of a conveyor belt's tail pulley. As the conveyor belt goes across its length, it'll take images of the conveyor belts and as such build up a 3D model of the entire thickness of the belt. So one issue that has been identified with this system is that dust kicked up from the back of the conveyor will deposit on the camera lens of the Warehawk system. So over time, this will degrade the quality of the images and as such, the accuracy and reliability of the system. So Warehawk have already taken steps to address this problem. So Shafiak 2020 is the research that this project builds upon, and a Warehawk sponsored study into mitigation techniques for preventing dust from depositing on a camera lens. So a number of methods were assessed, being ultrasonic vibration, applying some hydrophobic coating, or positive pressure air on the camera lens surface. So this identified a number of promising candidate solutions, but left a couple of questions, being, is this a realistic simulation of what happens in the field? So these methods were tested inside a dust chamber, and Shafiak 2020 was concluded in asking how these relate to the field and prompted further research into that area. So that said, my scope is to determine how we can measure dust deposition on an underside in the field and its effects on a camera's performance, and if this dust deposition can be characterized as some function of exposure to particulate matter, being dust. So the motivation behind this is that Shafiak 2020 was not entirely sure if, although it proved these methods worked in the chamber, would these actually translate to the field? So number one, it wasn't determined if a saturation point had been reached. So had the methods been tested under this kind of conditions where we would expect a steady state transmissivity invariant with respect to some variable. It was also unsure what that variable was, what kind of scale this would work on, whether this saturation slowing happens over the course of weeks or the course of hours or days of dust exposure. So how can all this all be answered? Well, number one is that we need field measurements. So to achieve this, there are a number of key requirements that I had to meet in producing the system, in acquiring these measurements. So number one, a field site had to be obtained. This must have to be a sufficiently dusty location on an industrial or mine site where we could regularly get in and access with permission from the site. We also had to develop field units, which were capable of measuring a camera's performance through some surface where dust is depositing, as well as measuring the covariates of dust deposition, so most importantly, airborne dust itself. The resources we had to put towards this, software and electrical design capabilities of Warehawk, as well as the dust chamber used in Shafiak 2020. So I'll now take you through a bit of the design process for the case of the field units. As I mentioned, there were two key requirements of these, being that it measured the degradation of camera performance. And obviously under these, we have a couple of sub-requirements, being that number one, it it has to isolate the effect of dust. We also have to be capturing the dust as deposited. So we have to make sure that the dust isn't being disturbed in some way between depositing and capture of the dust. Finally, we have to do this in some standardized formats so that we compare every measurement from every site to each other, obviously in some kind of standardized way. So there are a number of ways we could have gone about developing this kind of system. We could obviously be measuring in the field, so we could have a camera out in the field taking measurements through some of the same surface. We could have retrievable samples, so lay out a number of samples and collect them week by week, allowing dust to deposit on their undersides. An approach commonly taken in the literature for measuring dust deposition is to put out some sample surface and weigh it to determine its weight change, and then use some kind of proxy relationship to transmissivity through that. However, the method we ended up going for was the slide collection method, which I'll demonstrate now with an actual sample used in the field. So the samples were like this and positioned on a rail as so. Now, these are set out and collected a week at a time. And over this period, we would allow dust to accumulate on the bottom surface as such. And when it was ready for collection, we would come along with a partner slide and beat it like that. Now, what this does is this sandwiches in the dust there. So it's safe during transport, won't be disturbed. Now, when we're ready to take an image of it, we can remove the top slide, we can remove the bottom slide, revealing simply surface with dust sandwich in between there, with clean surfaces on either side, these outer surfaces serving to protect these surfaces through which the dust will be viewed. Similar thing can be seen there on the slide. So the field trials were run for 9 weeks in total. They were run on an industrial site in Kwinana next to an alumina bagging unit and an aluminium sulfate crusher. These were also installed on the units on the ECM roof, just as a reference unit to troubleshoot the units themselves. So they consisted of 2 major parts, being the sensor station and the slide station. I'll get into each of those now. So the sensor station itself consists of the sensor box and the data relay and collection box. Now the sensor box obviously just houses the sensors. We had 3 different dust sensors in there, each of a different make, obviously to provide redundancy both in number and design. And the temperature and humidity, we're also measuring temperature and humidity within the sensor box. So the sensor data was relayed to the data relay and collection box where it was stored, and we could then interface with this box via a Wi-Fi connection and download this data week to week, so we can troubleshoot any issues as they cropped up, as well as analyze this data. These were powered by a mains power from the plant, so we didn't have a single moment of loss of power. So you can see there to the right, that is the web page that you get when you connect to the unit's Wi-Fi. It allows you to download data from the box itself. So as I mentioned, there are a number of variables influencing dust deposition, and we obviously have to choose and control what we can because we are doing site measurements. So what we decided was relevant here is obviously we control for a lot of variables. So the locations themselves were inside a shed on the industrial site. So things like rain, wind speed, and wind direction could really be factored out in these kinds of environments. We're obviously still measuring humidity, and we're really interested primarily in dust. Obviously, we can exclude surface effects, as these are all acrylic slides at the same angle, just turning perfectly flat down. Obviously, side effects cannot be excluded. However, these are considered to be second order at best, just from a rough site survey. So the slide station is 10 clear acrylic slides suspended height above the ground on cinder blocks of a very sturdy design, not going to be knocked over or vibrate out of place. The slides themselves are held in place by bolts, so we can just seamlessly come up from the bottom and collect them without disturbing the other slides or the dust on the other side too much. And as I mentioned, we were trimming these slides weekly, so all 10 were put out there to begin with, and then we would come and collect each one each week, representing a progressive saturation of dust on the bottom of these slides. So once these were taken back to uni, we then analysed these in the Shaffiak 2020 dust chamber. This allowed, we used the same experimental setup essentially, and this allowed for a standardised measurement of each slide, keeping distance, position, lighting, and camera settings the same from measurement to measurement. So the actual metrics we were measuring were contrast resolution and transmissivity decrease from some control due to dust on the undersurface. So you see at the top there is an image taken through a completely clean control slide, and at the bottom there you see an image taken through a field sample. You can see on the right there the histogram of the grayscale values for each one. So we were simply just taking the mean, and the difference from the mean to the difference between the mean of the control and the field sample, and we're calling that the decrease in transmissivity. So the field units were able to perform remarkably well. We collected airborne dust over a 9-week period with minimal interruptions. So you can see at the top there, that's the alumina units, and at the bottom there's the alum units. You can see peaks daily there corresponding to the plant running up and down. We obviously ran into a number of minor issues. Number one being a software update in the earlier weeks just to correct some issue with not every data point being taken. We had the temperature and humidity sensor fail in one of the units, and we had a internal error calculation come up in one of the important sensors. However, this could be supplanted with some other data that's being collected adequately. So to bring it back, what we started with was we expected to see this kind of saturation behaviour where transmissivity decreases initially rapidly before tapering off to some steady state level with respect to dust exposure. However, what we saw in the field was essentially nothing like that. So you can see that there's essentially no relation between the decrease in transmissivity and the cumulative exposure to PM2.5 dust. Now, I've chosen to PM2.5. This is a call based on what the literature says, which suggests that particles of this size are both the most likely to deposit on a surface, as well as are the most likely to cause a drop in transmissivity. They're sufficiently large enough to do that. So what is to be said for this? Well, essentially what we're saying is that we have the slides samples are shown to be invariant in transmissivity after 1 week of exposure, and we're considering this as saturated. So further dust will not actually cause further decrease in transmissivity. So saturated, we're not seeing the expected progressive saturation over weeks and weeks like we anticipated. So possibly a timescale issue here, possibly some other issue entirely. Also notable is the slides we retrieved. We noted this pattern dust distribution on each one. So particularly you can see week 1, week 5, these kinds of circles where lots of dust seems to be accumulating at one point. We were essentially just expecting some kind of uniform caked layered dust distribution as typically occurs on an over surface. So we can come back, number one, and interrogate the variables. So coming back here, is there something we missed out? Obviously we were capturing those dust variables, but it's invariant with respect to that. Could it be the site variables? We cannot be sure of that either. Some of these things have to be ruled out, possibly some other variable we have not considered whatsoever. So coming back to the method itself as well. So can dust itself adequately deposit on the bottom of these slides, or is there some issue that's preventing dust from depositing? Is the dust of the correct size and type to actually deposit on the underside, which is dealing dust that is not preferentially going to deposit on an underside, and we can't expect something else. Is our measurement itself sensitive to dust on the slide? So is it essentially just giving us random things, or is it giving us something that can be logically related to dust on an underside as transmissivity? Does our dust sensor station monitor dust in a way that correlates with dust deposition? So is the issue with the sensor station itself, and it's not actually accurately telling us what's going on with dust in the air? So we're able to look at this through the assess all these claims really through the dust chamber setup used in Sheffield 2020. So this is revamped for our purposes, and we're able to conduct a number of measurements which really illuminates what's going on here. So what you're seeing are the saturation curves for a number of experiments run in the dust chamber using our slides. So these slides were able to be saturated with the camera taking intermittent photos across the saturation of the slides. So you do see this saturation behavior, as we had anticipated, come back. So perhaps saving itself here. However, quite interestingly, you see that although these all experience the same cumulative PM 2.5 essentially, these all have a totally variance decreases in transmissivity. Perhaps even further interesting is that at different rates of dust agitation, so these KPAs are referencing the pressure of a dust agitator inlet, we're not seeing any kind of correlation there as well between the transmissivity decrease. So this really leads us, so we also come back here, to the dust samples themselves. And just like in the field, we see these same similar characteristic patterns on each surface. So the real conclusion here is what is going on is likely not the side, because we didn't see, we saw this kind of same pattern replicated both in the test dust chamber and on two different site locations. But most likely what we're looking at is the variance we see between slides is due to some actual surface effects of the slides that we did not account for initially. So what does this all mean? Well, number one, we consider our design for measuring dust deposition and particulate matter in the field as being robust. We was correct, and we essentially just ran into an issue with the slides surface factor, which had not been accounted for. PM 2.5 clearly plays a predictive factor when all else is equal. So as you saw on that previous slide, you do see that saturation behavior. However, the actual steady state point will be set by some surface factor and is not determined by particulate matter exposure. And we can also say that the dust chamber itself represents a near worst case scenario from a dust deposition standpoint. So we're clearly able to see that we reach saturation very quickly in the dust chamber across all the samples, so that if you get even further dust exposure, like you might see in the field, even in the worst case scenario, even a really high dust scenario, it's likely going to be something similar to what might be experienced in the dust chamber. So to put the final point here, this reinforces the findings of Sheffield 2020. And future work potentially here, obviously more to build off on, enhanced field testing, so testing at more regular intervals, potentially hours to days of exposure, and also taking more samples per interval, just so we can fill out that data a bit more. Number two would also be interestingly to explore how the surface effects mattered. So how would a different cleaning and coating effects, how different cleaning and coating procedures for slides affect deposition and whatever surface steady state surface saturation you arrive at. Also being able to see if we're able to standardize the surface, so assure they all have the same coating, same cleaning procedure applied. Does this effect of the variance between saturated samples disappear and they all start to kind of coincide with one steady state transmissivity? That is all. Thank you very much for listening to my presentation.